In this video, I'm going to show you how to work an example problem that's very similar to your problem 1 in problem set number 3. So here on the screen right now you see a blank version of your problem set where we needed to solve for the aerodynamic conductance and sensible and latent heat flux from an alfalfa canopy. And over here on the right you see my example that I'm going to work through. Now I used a program called MATLAB and then a publish feature, but I think you'll be able to follow right along and see how I basically worked through the exact same set of questions that are on your problem set. So let's go down to the input parameters for the problem that I'm working. I've got crop height, in this case a grass that's 12 centimeters tall, air temperature, relative humidity, wind speed, the height of the wind speed measurement, the altitude, it's a typo right there, it shouldn't be the pressure, it should be the altitude in meters, temperature of the canopy, 27 degrees, canopy conductance, remember this is the integrated effect of all the stomata on the canopy, specific heat of air, latent heat of vaporization, and the molecular weight of water. These last three are just kind of constants that you should probably always have on any kind of study sheet or things that are going to be used for the exam, for example. So the first thing we want to do is try to estimate the aerodynamic conductance, and we're going to need a couple of parameters to do that. In my problem, I just had my altitude, I didn't have the pressure. You actually have the pressure in your homework already, but if you didn't have the pressure, if you just had the altitude, we use our familiar formula here where we can estimate atmospheric pressure from altitude. And when I did that, I got 84.36 kilopascals. That's pretty typical for our elevation here on the Front Range of Colorado. Another parameter I'm going to need to calculate this aerodynamic turbulent boundary layer conductance is the molar density of air. And that formula is in chapter 3 of the textbook. Here it is shown again. You need the atmospheric pressure, PA, and you need the air temperature. And we're converting it here in degrees Kelvin. This is basically a re-expression of the Boyle-Charles law. And so you can see for us, our pressure here is 84.36 and my air temperature was 30 degrees. And if you plug those in, I get a molar density of 33.46 moles per cubic meter. So you would need to do that for your problem where your pressure is already given and your air temperature is also 30 degrees. So you should get something very close to that number. Also, to calculate aerodynamic conductance, we're going to need our roughness parameters. Displacement height, roughness length for momentum, and roughness length for heat. All those can be computed from the height of the vegetation. And you can see me doing those here using, in my case, a height of 0.12 meters or 12 centimeters. Your canopy is 50 centimeters tall, so your numbers are going to be larger. Now I have everything I need to calculate aerodynamic conductance. This is the formula. It's in chapter 7. We take the von Karman's constant squared times our molar density times the wind speed. And then down here we have two log terms that have the height at which the wind speed was measured. This is Z right here is the height where wind speed was measured minus displacement height over Zm times the log Z minus D again, but in the second one we use the roughness length for heat. And I got approximately 0.55 moles per meter squared per second. Now I ask you to convert that to meters per second. All you have to do, remember you can always convert a conductance expressed as moles per meter squared per second 2 meters per second just by dividing by the molar density. So You just take your answer here and divide by rho hat from up here. And when you do that, I got 0.0164. Okay. Now that we have our conductance for heat here, we can calculate sensible heat flux, and that's our aerodynamic conductance for heat times the specific heat of air times the temperature difference between the canopy and the air. So GHA comes from here. CP was one of our constants up top, 29.3. And you plug those in there, and I got minus 48.22 watts per meter squared. That would be the answer, corresponding answer in your problem here. Because the canopy is cooler than the air, sensible heat is moving toward the surface, and that's why it's negative. Right? The canopy was 28 degrees, or in this case 27 degrees, and the air temperature was 30 degrees. So warm air is blowing over a cool canopy and transferring sensible heat flux to the surface. Okay, we've got sensible heat flux. Now we need to start thinking about how we're going to get the water vapor flux, and that's going to require us to calculate the total conductance. The total conductance, because remember water vapors has to travel through the stomates, then through the boundary layers. So it's like conductors in series. So we use this formula. This was out of chapter 6 in the textbook. And we need both the conductance for heat, aerodynamic conductance that we just calculated, and we also need the canopy conductance, the effect of the stomates. That was a given up here, 0.4. It's also given in your problem. So we plug that in there and we get 0.23 basically moles per meter squared per second. Again, we can convert that to meters per second just by dividing by molar density. So that's how you would do it. We can calculate the vapor pressure at air temperature and the vapor pressure of the air. You guys have done this already a lot of times. So we just take our air temperature, calculate the saturation vapor pressure at air temperature, multiply by relative humidity, and we get the vapor pressure of the air. We can convert that to mole fraction by dividing by total atmospheric pressure, right, which in your case was 84.1. So that's our mole fraction of water, moles of water vapor per mole of air. Now we need to calculate the saturation vapor pressure at canopy temperature. Again, we use our same Teton style formula, except now canopy temperature is in here instead of air temperature. Okay, and we want the saturation vapor pressure, right? So here we just say the vapor pressure inside the leaves of the canopy is at 100% relative humidity, and we get 3.5 kilopascals. Remember, you can always look these up from the table in the back of the book also and avoid having to calculate this and use this formula. Again, to get it into mole fraction, we just divide by total atmospheric pressure. So there we have our moles per mole. This is like the saturated mole fraction inside the leaf. And now we're finally ready to estimate water vapor flux. Okay, so we're basically down to this place in your homework. That's pretty simple. In this case, our molar flux is just the total molar conductance times the difference in the mole fraction between inside the canopy and the air. Okay, the numbers that we just calculated. And I get a molar flux of 0.0074 moles of water per meter squared per second. I can convert that to a mass flux by multiplying by the molecular weight of water, 18 grams per mole, except I ask for that in kilograms per meter squared, so you're going to need to multiply it by the molecular weight of water and divide by 1,000, and it gave me my rate. So this is basically the amount of water vapor that's leaving a meter squared of canopy, if you're thinking square meter of canopy if you're thinking about if you're standing out in the field. We can convert that to latent heat of vaporization just by multiplying our evaporation rate times the latent heat of vaporization. Okay, I'm going to use the molar version, so I'm going to take this number and multiply it by the latent heat of vaporization, which is about 44,000 joules per mole. That's how much energy it takes to evaporate a mole of water. And I get a latent heat flux of 327 watts per meter squared. Okay, that's very reasonable. I'm guessing, just guessing, looking at your numbers, you might get a number slightly larger than that. So again, we've expressed it in terms of a mass flux and in terms of an energy, but a lot of us are interested in hydrology. We want to relate it back to a depth of water. Recall that a kilogram per meter squared of water is equal to 1 millimeter depth of water. So all we have to do is take our evaporation that we calculated in terms of mass, kilograms per meter squared, and multiply it, that's kilograms per meter squared per second, and multiply it by the number of seconds over 12 hours. So that's what I did here. And I got a depth of water of 5.78 millimeters. Okay, so that's about a 1/4 inch of water. For those of you that know about turf grass water use, that's pretty common in the summer. A lot of yards use about a 1/4 inch of water per day, and that's what you have to apply with your irrigation system if you want to keep it well watered. So again, this document that I'm using here on the right, I posted that on Canvas, so you can download that and look at that, as well as watch this video and look at these particular set of calculations. I think that should help you work down through all your questions here on the homework. The extra credit part, I think you can easily figure out just by looking at the textbook.